Yes. Coulomb's law. Let's pretend that didn't happen. Right. What? Coulomb's law. You got this? I don't know. Somebody moved it, I think. Okay, continue. Right. So you remember that we have an electric field around a charge. Anyways, Coulomb's law is a way to calculate the force. Let me see if I can. Maybe I can draw it. Anyways, do you remember, before you write this down, remember you have the formula F equals QE? Yeah? Maybe I can prove it. Let me see. So you remember that we have F equals QE. That's when we have a point and an electric field. Come on, open. Everything's so slow. There we go. I have to use this for a moment. Here we go. Okay, back to this. So if you remember, nope, still not working. There we go. Okay, we have, can you see this okay? Yeah. F equals QE. So this is when we have our Q here, and there's some electric field here. We'll call this one Q1, and we'll call this one here Q2. Do you remember the formula for the electric field strength for Q2? E equals, does anyone remember? Or you can check. 1 over 4 pi, does this look familiar? Epsilon Q2 over, I remember this? These formulas?
No, which chapter? Yeah.
Oh, just recently. Yeah. What's the lesson called? Electric field strength formulas. Anyways, doesn't matter. You see it now? Yeah. Anyways, you can put. Can you show Grace? I gave you the formula.
Oh yeah, that's it now.
Great.
It's Q over R2, right?
Yeah. So you can put these together, and you get F equals 1 over 4 pi epsilon 0 Q1 Q2 over R squared, if you put this in here for E. but this is just a constant, so you could write it like this: F equals K Q1 Q2 over R squared. And this is actually Coulomb's law for how much force there is between two charges. The force of attraction or repulsion between two charges. Now I'll put it up on the notes here. This is it here. F is the force, Q are the charges, R is the distance, and K is the constant. I just wanted to give you a little proof of this. Constant. There's its value. Continue? No. Proof? Small proof. If you want, you can write it down. Yeah? Hang on, what do you need to write down? You just need the value of K?
Yeah.
Okay, one sec. 8.99 10 to the 9. Okay. No, I think, Amanda, you can watch this proof from the video, I think. Yeah, you can leave a space for it. Yeah. Okay, continue. So let's look at this example. Actually, we've kind of seen this one before. Does anyone remember the answer? So, if I go back here, here is my proton, here is my electron. There's a force here. That's equal to K Q1 Q2 over R squared. I'm sorry, I should keep my Q's the same. Q1 Q2 over R squared. And here there's a force, K Q1 Q2 over R squared. Are they the same or are they different? What do you think? They're the same actually, because the K's are the same, the R's are the same, and the charges are the same. So if the force is the same between the proton and the neutron, why does between the proton and the electron, why does the electron move and not the proton? Yeah, because the proton is much heavier than the electron. So even though the force is the same, the acceleration is not the same. Which has more acceleration? Electron. Why?
Light.
It's lighter, less mass. Yeah. Okay. Anyway, so if you remember, we actually talked about this in homework before. Do you remember? Okay, that's okay. Trust me, we did. Okay. When one charge Q is trapped in a circular order by another charge q. So the reason I have a small q and a big Q is I want you to remember that for this problem, the small q is smaller than the big Q, usually. Then it will have negative potential energy. So do you remember we have positive, 0, and negative potential energy. So if the potential energy is positive, what does that mean? Yeah, usually it's higher. It can do work. If the potential energy is 0,
No.
it's free. It's on the ground. And if it's negative, it means it's trapped. And this is something you'll do in chemistry as well. Let me go back here now for a second. So do you remember this from mechanics? If the potential energy is positive, the person falling, it can do work. If the potential energy is 0, it's free. And if the potential energy is negative, it's trapped. It needs energy to be free. So, if you have a proton and an electron like this, here's the proton and here is the electron. The electron is trapped. It's trapped by the proton. It's not free. So, we say that this electron has negative potential energy. Because it's like Earth and Moon. You know, the Moon can't go anywhere. It's trapped with the Earth. Just like with the proton and electron. You know this from chemistry. Remember ionization? So ionization, you have to give it energy to free the electron. Because the electron is trapped. It has negative potential energy. Yeah? So for example, if the potential energy equals -1 joule, how much energy does this electron need to be freed?
1 joule.
It needs 1 joule. The ionization energy. Just like in chemistry. Yeah? So this is the formula to calculate the potential energy. You don't have to write small q and big Q. You can write Q1 and Q2 if you want. And you see the minus is there because it's trapped. For this, yes. Yes.
My answer is -2.
Yes. Continue?
Not
Not
yet.
yet. We don't care about that minus so much. That minus is just for the direction, but we don't care about that. We just want to know how big the voltage is. Don't say you don't care. You can just say the total voltage is.
And this is positive?
If you want, yeah. Coulomb's law gives the size of the force between two charges. This force is the force between charges. It's one of the 4 forces in nature. There's 4 forces in nature. Coulomb's law is an example of an inverse square law in physics. These are very common in physics. It's worth examining why that is. Let's imagine why. Okay, so I'll just go back to the law for a second. Where's it gone? So you notice that down the bottom there's an r squared. Yeah? This is very common in physics. You accidentally saw Newton's law, and you notice that Newton's law also has an r squared at the bottom.
But
Yeah?
potential energy there was no.
No, it's not in that one. Yeah, in the force there is. And what I want to say is, in physics, it's actually very common to have a formula with the r squared in the bottom. So remember I said you accidentally saw the Newton's law, but if you still have it, you notice it also has an r squared down the bottom. Okay? And this is because you can imagine as the charges get further apart, is there more force or is there less force? There's less force. But does anybody know why maybe it's r squared and not r? No? It's something to do with a circle, yeah. Yeah. Let's have a look. This, which formula?
No.
Are you sure? Okay. Where am I? Right, so let's have a look here at why these formulas are so common in physics. So let's make up an example. You want a formula for how bad somebody smells. If they smell bad, if they smell good, whatever, okay? So, let's say they smell bad. Yes? Now, as you get further away, is it stronger or weaker? It's weaker, isn't it? You can think about the smell coming out like this. But the smell moves outwards like a ball. You know, like for example, if I make them smaller. Let's make them smaller. His smell moves out like this, doesn't it? So it's the same smell each time, but it gets divided over a bigger circle, a bigger sphere. So here it's a small ball, but here it's a large ball. So what's happening is the smell is getting divided by the area of the ball. Do you remember what the formula for the area of the ball is? Maybe from middle school? It's 4 pi r squared. Squared. So what's happening is the smell is getting divided by r squared.
Why not that 4 pi?
And the 4 pi is there, but the 4 pi gets moved into the constant in the formula. So for example, if there was a constant here in the formula, the 4 pi would just get pulled into the value of the constant. So if you think about it, a lot of things in physics are like that. Smell, gravity force, electric force, that they all spread out. This is why the r squared is so common for this moving out problem. You don't need to know this for the exam, but I just wanted to explain why r squared is so common. There's actually a reason for it. Let's go back. And finally, before we look at an example, I want you to notice how big the value of k is. It's very big, isn't it? 8.99 times 10 to the 9. It's It's very big. So this is a very strong force. Yeah.
What is E what is good?
That's the name of a law that has an R squared in the bottom. You don't need this for the exam. I just thought it'd be interesting. Okay, let's have a look at our first example. What is the force between a proton and an electron which are 0.1 nanometers apart? Sorry, there you go. Okay. Yeah, but still not working. There you go. You got this? Yeah? Okay. Let's have a look at the answer. So you have your proton, you have your electron, and there's a force here, and there's a force here. And we can calculate the force by using Coulomb's law, K, Q1, Q2 over R squared. And the K is 8.99 times 10 to the, what did I say? 9, is it? And what's the charge of a proton and an electron? It's 1.67. What is it? Do I have it on my calculator here?
Oh, I found it.
You found it? What is it, so?
That's not it. Oh, is it 1.6 times 10 to the power of negative 19?
Yes, I guess so. 1.6 times 10 to the minus 19 times 1.6 times 10 to the minus 19. And what's the distance? 0.1 nanometer squared. Okay, what's this? Can you calculate that? I don't have my calculator today.
It's actually 1.602 by the
Oh, it doesn't matter now.
but 100 is 96.
Yeah, but that's just for the direction. The one is positive and one is negative tells us that they're being attracted to each other. Great. What you doing? Good.
But do you not have to write it?
No.
2 plus 30144 multiplied 10 to the power 96.
What you can just write, Hareen, is you can just write the direction, which is towards each other. Towards each other, attracted. Too bad.
No.
How much? Okay.
No more.
No milk in it?
No more.
No more. Okay. Next. Tastes like water? Disgraceful. Okay, next one. how long does it take an electron to orbit a proton which is orbiting in a circle of radius 0.2 nanometers? So what you've got here is a proton and an electron, is it? Yeah, and they're going around like this. And I want the time for one circle. Do you understand? Yeah. Yeah? I'll do it now. I just want to make sure you understand what I'm asking. Okay, can I do this one now? Yeah. Yeah. The time for. Yeah. Yes, correct. So let's have a look at it.
Who could give the example to give the case
Yes. No, give it. Yes. Okay, so here we've got force, and here we've got force, and it's moving in a circle. So you have F equals K, Q1 over Q1 Q2 over R squared. However, because it's moving in a circle, you can use the circular motion force. Do you remember what that is? M omega squared or. Now your one is mv squared over or is the other one. Okay. So we can use both of these and we get this formula. Is this the mass of the electron or the proton? Very good. Mass of the electron. Because that's the one that's moving. Yeah? So we get the omega will equal K Q1 Q2 over mass of the electron. I'll get rid of that E, I don't need to write it. We know it's electron. Or cubed. Square root. But what does omega equal? But omega equals 2 pi over t. So then what does so then that means t equals 2 pi over omega. So we can get this formula. T is 2 pi root k q1 q2 over upside down, m or cubed over k q1 q2. So this is how we can calculate the time. Nice. I'll calculate it. 2 pi root fraction m. That's number 3. What did I say the radius was? 0.2 nanometers. And then K is 8.99 times 10 power 9. And then okay. So you get 1.12 10 to the minus 15 as the answer. I'll write it here. Yes, Grace, what are you asking me? I don't know, it's on my calculator. Here, I'll show you on yours. This is the mass of the electron. Shift. Shift. 7. And then number 3, O3. The radius is in this question. 10 to the minus 9. But then, wait, no. Cubed. Yeah, and then 8.99 times 10 to the power of 9. And then mass of the charge of the proton. Charge of proton, charge of electron. Yeah, equals. Very interesting. Okay, continue. Why is this? Alright, can you try this one for me? You can use the potential energy formula. Huh? Second, yes. Yeah? We have a look at it? Okay. So this electron is trapped, so it has potential energy, yes? The potential energy it has is equal to minus K Q1 Q2 over R squared. Over R. So that will equal minus 8.99 times 10 to the 9 times 1.6, whatever it is on the calculator. I'm just going to write in E and E because that's what's on the calculator. And 0.15 nanometers. Yep.
But one is positive, one is negative.
Again, we want the answer to be negative in total. So really, I should have this around it in the formula, but I didn't want to complicate things because I'm not sure if you've done that in maths yet. Have you?
Yeah.
You have done it? Are you sure? What's it called then?
Modulus.
Yeah. or absolute. Okay. Did you get an answer?
E is constant.
Yeah. The charge of an electron. -8. Yes? So that would be minus 15.3 nanojoules. So that's how much energy you need to free the electron, the ionization energy.
Why is it nanojoule?
Hmm?
I got over 19. I got minus 18.
Oh, sorry, Grace. Something went wrong. What is it? Should be minus
1.54 times 10 to the power of minus 18.
Okay. Why do you keep forgetting this word? Divide.
Something difficult.
Divide. Okay, continue.
No.
What?
Wait.
Continue.
Yeah.
Okay, there's the homework there.
Why do kids don't work?
How or why?
Why?
To fit in more questions. You think that's tiny? Okay, can I close this?
Can I use the bathroom?
Yes. Now, what we'll do now for a little bit.